Okay, so for today's lecture, we're going to try something slightly different. Instead of just producing slides directly from the book, what I intend to do is walk through the entirety of the data lab and see if we can't have some conversations or investigate some of the solutions and just make sure everyone understands what the problem was, what the motivation behind the lab was. And since you have worked on this now for some time, if you got stuck on any particular problem, we could really kind of dig deep and investigate what these solutions are. Now, I'll state this now, and I'll restate it later. The solutions I'm going to provide to you are not actually in C, right? So I'm not giving you the direct answer. I'll show you analogous solutions in Python. But you'll see that I tried to keep my Python solutions relatively close enough to C so they provide adequate hints. Okay, so let's hit up the slide deck. And also let me add the chat in case we have students who want to ask from the online world. Okay, so this is going to be Data Lab. The motivation behind Data Lab was to really investigate concepts related to Boolean algebra and bit level representations. So, of course, the purpose of this assignment was to familiarize you all with Boolean algebra, which you should have had some exposure with in the prior class, to understand some bit level representation of our integers and to solve some programming puzzles to understand our machine level representations of our data. This is also a great opportunity for us to learn how to use our bitwise operations in C, since that's not typically operators that you use so prevalently in higher level languages like Java.
So we're supposed to learn Boolean algebra in that one, or
I would think so. Do you not cover any Boolean algebra concepts in
spring? All we did really was walk through, use Visual Studio to step through it and look at registers.
Good to know. Well, one of the things that hopefully moving forward is we'll take like the bulk half of what we've covered so far in this class and pivot it into the assembly class so that we can then move more rapidly into the systems level stuff in this class, which will then allow us to make sure you're in a good place for your OS class. But that's okay, because we'll walk through all the Boolean algebra problems from this lab inside this lecture. Okay, so the recommended readings from the textbook that you could use for this lab are 2.1 and 2.2. So how do we go ahead and work on this lab if you haven't worked on it yet? Well, use web terminal, right? Just use the guacamole GUI instance. That's going to be the easiest way for us to do anything for our systems class. So what's that going to look like? Well, using a web browser, we can access our systems lab Ubuntu environment, right? And then we're going to in order to start on this lab in particular, once we've logged into our web terminal, and everyone's done that, right? I would hope at this point, everyone's learned how to do that. And so if you go to web terminal, right, .cs.uno.edu, and if you go to that, it should give you the option here to be able to go to the systems lab. When you launch into that, okay. Okay, well, this is we're going to pretend like we can easily access this. But presumably, if you go to that URL and you don't get limited, you should be able to open up your environment, a windowed version of your environment that's going to have all of our systems level content available. And so that's going to make it much easier for us to get the necessary files and such. The easiest way to get the necessary files for each of the labs into your systems lab environment that you log in with your UNO credentials is to launch in the web browser, the web terminal instance, And then now you have an OS instance inside of your web browser. So you navigate to that web browser. So now we're talking about nested web browsers. So inside of applications, you can go to internet. Inside of internet, you can either pick Chrome or Firefox for this particular lab. It doesn't matter. When you open that up, go to autolab.cs.uno.edu. It should look like this. You then use your UNO credentials to be able to log in. If you do that, it should bring you to something like this. That's going to take you to our 2467 System Programming Concepts Auto Lab. This particular Auto Lab we're doing is Data Lab. So you would click on the Data Lab instance here. And so if I then scroll down, I can find all the attachments that's necessary for this lab. So in this instance, I would want this datalab.handout.tar. And then if you want, you could also grab the datalab.pdf document for your Ubuntu instance in case there's any copy pasting you want to do from that. But it might not be necessary if you just print it out or if you follow it along on a different computer or on a tablet or on your mobile phone or whatever else you have, so that you can kind of have a workspace to work from and a document to kind of look at. Anyways, the important part is going to be the perfunctory files, so which are going to be tarred. You can then go into like your downloads or move them wherever you want. You could either use either the GUI, or I would prefer if you use the command line tools, right? Because this is a systems class. So presumably you can open up a terminal and move everything you need and investigate and check the contents of that. But I give you illustrations of both, of what is inside of our tar file, what you start with. Okay, so now that we've talked about how you get the necessary files, let's take a quick overview of the puzzles of this data lab. So there's an objective here, right? You have to use only straight line code for integer puzzles. So when I say straight line, that means that you can't have any control flow constructs, no if statements, no for loops, no while loops, right? So we're also limited to the C arithmetic and logical operators. And in fact, each problem will specify in particular what operators you're allowed to use. So some problems will allow more or less operators than others, because sometimes you're trying to emulate a behavior and operator without using that actual operator. So obviously our restrictions are you don't use loops, no conditionals, you can only use these particular primitive operators, and you can't use any constant longer than 8 bits. The reason why that's a constraint is one of the problems is to try to make a binary string that's larger than 8 bits. So clearly you can't just hard code that. Okay, so let's take a look at the actual puzzle details for this lab then. We could break this lab into 3 different types of operations or puzzles. We have our logical puzzles. When I say logical puzzles, that revolves around Boolean data types, right? I think the actual lab calls it Boolean data types, but I like to map that more in the denotationally as a logical resolution, a logical expression. And so for these, you could say we have the bit or, the bit and, the bit XOR, the is not equal, the copy least significant bit or LSB, the special bits, the conditional, and the bit parity. So that's what? That's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 problems that make up your logical puzzles, and each one is allocated a different number of points based off of its difficulty. And here inside this column is the max number of operations that you're allowed to use to solve this problem. And of course, if you can do it in less operations, then that's even better. But you can't exceed any of the amount stated here. And of course, a quick description of what each one of these puzzles is targeting for you to do. We'll talk more about those when we start looking at the starter code that we're given and the actual potential solution that we can use to solve this. Now, by all means, when we get into the solutions, I'm not saying that my solution is the de facto standard, right? There might be more than one way to skin a cat. Oh, that's an awful expression. There might be more than one way to solve a problem. but I will show you a possible way, right? So that if you got stuck, we can discuss a solution. Okay, so the second part of the puzzles are going to be the arithmetic puzzles. So these are the problems that deal with arithmetic properties of numbers. They can involve operations like addition or subtraction or finding a maximum value, negation, and checking the sign of numbers. These operations change the numeric interpretation of our bits. So in particular, we're going to have 1, 2, 3, 4, 5, 6, 7, 8 of these problems. In particular, these functions are already stubbed out for you as -1, T max, negate, is negative, is positive, bang, add okay, and absolute value or abs val. And again, we'll go into more detail when we start to go ahead and discuss solution outcomes. And lastly, and so this was the bonus component of this lab, are the bitwise puzzles. So these are the problems that primarily deal with manipulating the individual bits or groups of bits within our numbers. They can involve operations like counting the number of set bits, swapping certain bits, and shifting bits. They're more about manipulating the bit patterns directly than what the other two sets of problems are. And these are only composed of 3 puzzles: the byte swap, where you swap the nth and nth byte inside of a binary string; a bit count, which is going to return the count of number of ones in a byte word; and finally, a logical shift, which shifts x to the right by n using a logical shift. So let's move on. And we'll talk more in detail for each individual one of those as we approach the solutions, but this just broadly speaks to the classifications of these problems. Okay, so the evaluation criteria, right? So you got to pass all the tests through Autolab. That's one of the nice things about Autolab. You should only use the legal operators, right? And you should produce explanatory comments inside your code to illustrate that you understand how your code works. Okay, so let's talk about Autolab and how the Autograding tool works. So the assignment provides a set of tools to help students check the correctness of their work. So it's not just that Autolab will autograde your work, but if you wanted to evaluate to see what Autograde was going to give to you, did everyone realize that there was auto-grading tools that you could run locally? Perfect. And so these tools will ensure that the solution adheres to the given requirements, and it'll give you a little bit of feedback. So just to highlight this, they have btest, which was one of those files that we had when we first went ahead and downloaded all of our handout material. So if we go and navigate into our directory that contains our handout code, we can just make it. And then if we execute btest, then btest will tell us how well we went ahead and implemented. So for instance, to give you an illustration of what this looks like, after I call a make and then run the btest executable, and with the stubbed out implementation, you'll see I'm going to get a lot of fails from the get-go and messages as to why I failed. So this kind of gives you an understanding of what Autolab is doing in the background to evaluate your code. Now, on the flip side, suppose I fully implemented all of my solutions and then I remake everything and then rerun my application, my btest application. My output would then look like this, where it will then show the points that I get for each of the problems and then give me my total point score. So this is what you get with the stubbed out code. This is what you get with a fully implemented code.
With the btest, if you just recompile bits.c, you don't need to remake everything.
Yeah, that's true. Okay. You also have DLC. That's going to be our coding rules checker. So this is going to verify the compliance with the coding rules for each puzzle, because remember, it's not just about getting a particular solution, but adhering to a particular set of rules for your solution. So you can test to ensure that your solution meets the requirements that's stipulated in each of the function headers. in the comments. So when we run this, so we would run our application DLC and then pass it bits.c. That's the file that we're implementing on. Then the behavior should be that it runs silently unless it detects an issue, such as an illegal operator, too many operators, or non-straight line code in an integer puzzle, right? All the things that we said are violations or restrictions, this looks for. And so and some examples of what this looks like on both a successful run and an unsuccessful run. So if I call DLC on bit C, and if it is implemented correctly, it'll just silently execute and then prompt and wait and then deliver another like system level prompt on what's the next thing I want to do. Now, on an unsuccessful run, when it detects a violation inside of your code, here's some examples where it shows, oh, on this particular instance, special bits, 6 operators exceed the max of 3 that was allowed there. Or in this instance, on bit count, 42 operators exceed that max of 40. And then finally, you have the comprehensive evaluation tool, which uses both B-test and DLC to compute the correctness. And here you could just go ahead and run your executable driver.pl, which is a Perl script, which if I had enough time, I would refactor all the Perl scripts to Python scripts, just because I would want to do that. Okay, but I'm not going to do that, not this semester. So we'll deal with some Perl as for some of our system level scripting. Now, if I were to run that, I would execute that, and this is going to be the output I should get from that. Here you could see I have 0 out of 50 points if I try to run this with my initial stubbed out implementation that I haven't added any code to. And here, this will be the implementation that I would get once I've implemented everything. Okay. And then in terms of hand-ins, make sure once you've evaluated and you're satisfied with running everything through your systems lab and you've checked all the testing tools that's made available to you, you can then submit to Autolab. Or you can just use Autolab as your testing tool because you're not limited to the number of submissions you have. So you could always just keep, if you want to go through the submission process each time, you can do that as well. You know, it's up to you. It might be a little bit more work to have to submit it to Autolab each time because you probably have to like pull the document and like submit it into a little box and then hit a check that says something like, you know, this is your work or something, and then hit the submit. But that is another viable way of seeing how many points you get. And of course, there's a scoreboard. This is designed as a nice fun thing for you to be able to see how you kind of compare amongst the entire rest of the class. And of course, you can go ahead and create a nickname that's not your real name, so only you yourself know where you compare with everyone else, and that allows you to kind of be anonymous. Okay. And obviously some advice for the Autolab to actually work, or for all of the auto evaluations to work. You shouldn't be using standard in out. You shouldn't be using printfs, right? Because you could do that for debugging purposes, but when you go to evaluate your grade, anything that you're putting into the system.in or system.out could potentially pollute the ability to actually evaluate a grade, because we're just looking for the actual returned data values that are coming from these functions. Okay, so now let's start talking about our starter code, what we start with, and then possible solutions for each of these problems. So we'll just go and walk right down. So our starter code for the very first problem was bit or. And so the description for this problem is that we want to do X or Y, but with the constraint that we're only allowed to use the bitwise and the bitwise negation operations, right? So so each one of the stubbed out implementations produces a little example that illustrates when this function is called with these inputs, this is a expected output. So the expected input on this instance would be, say, for instance, 6 and 5, then the result would be 7. And when we're thinking about this, we're viewing these as integer numbers, but keep in mind, we're doing bitwise operations. So you have to be thinking of your value of 5, your value of 6 as binary strings to figure out how it's going to then result with a bitwise OR operation. Okay, so this one is a rating of 1. The first couple ones are going to be relatively simple, right? So the initial implementation that's given to us is just going to go ahead and return back a value of 2. I think that's true for all of them, right? They just return 2. So clearly, none of the current implementations you're given are going to be accurate, but we're going to see what we're starting with. Now, the starter code, I'm going to keep as C, as you can tell. That way you can remind yourself what is the problem, what is the specification, and what is the parameters that are getting passed in. Okay, so the concept that's going to drive this solution is going to be utilizing De Morgan's law. So since we can't use the OR directly, but we're allowed to use negation and bitwise ampersand, and then De Morgan's law allows us to use those two identities to transform into an OR operation. And it's the inverse. Like the next problem will be an and it's going to be a similar concept. Was everyone able to effectively have success with this one for the most part? And so just to see how this process is going to go, I have my Python solution here. So with my Python solution, given that X and Y, so let's note some things about Python first and foremost, because I'm now going to show you example solutions in a different language. So let me establish what you're looking at. You're going to see inside of my header here is going to be my function declaration. So in Python, I can declare a function using the keyword def. So I'm defining something. I'm defining a function. So def allows me to then create a label for my function. So another thing I'm going to state is also, as you can tell, Python is a loosely typed language. So whereas C and Java are strongly typed, you have to declare what type of data your variables are. You have to declare what type of data your parameters are, and you have to define what type of data your return values are. I don't have to do any of that inside of Python. So notice there is no return type inside of my function header, inside of my function declaration inside of Python. I just define a name for my function. So then this is going to be bit OR. That's the name for this function. Now in my parameter list, X, comma, Y, 2 parameters. No data type. Okay. So with that said, notice we don't specify return type, but we have a return type in Python by just returning something. Okay, so with that said, let's look at the logic, because the idea here is I want to show you the logic behind some of these solutions. So the first step we want to do is we want to invert our X using the bitwise NOT operation. So I'm just going to save that into a variable here so that I can kind of break this logic down over a set of lines. So we're going to get a NOT X. And then we're going to do the same thing. We're going to invert our Y using the bitwise NOT operation. So I'm going to use that operation, just store it in a variable, not Y, to indicate that we've had an operation. So we kind of break the logic down piece by piece. Then what I'm going to do is I'm going to use that bitwise AND operation with my inverted X and my inverted Y. So here I'm going to do my not X and not Y. And now that's going to produce my AND result on the negated or the inverted X and Ys. And so then I invert the result from the previous step to obtain the final result. So then I apply this on that solution, and that's going to be treated as a OR solution. And again, the driving principle behind why this works is De Morgan's law. It should be a concept that was taught in discrete mathematics, if I'm not mistaken, right? Because I think the first probably month of discrete mathematics, you go into Boolean logic. You probably go into symbolic logic, looking at truth tables and being able to convert between your ands and ors and XORs and things like that. So just a name for what this technique is, again, is De Morgan's law on the tool that we use to do that transformation. Mhm.
Is it the Python version of the big one?
Yes.
Okay.
Yeah, this is the Python implementation. So if you solve this problem, you could probably see it's very similar to how you probably solved it in C. Slightly different because of the syntax, but the logic should be the same. In fact, now let's test this out. I have this function here. If I go into my terminal here and type in, I'm going to use Python 3. Okay, if I'm going to paste that in there, for each one of these possible solutions, I created tester cases. So I have, for instance, 6 and 5. This is the one that was given to us. We should get 7. But then I did some more cases. 0 and 0 should be 0. 0 and 1 should be 1. 1 and 0 should be 1. 1 and 1 should be 1. Okay. And then I run through my test cases. I pass them as parameters into my function bit or, and I just print out the results. So just to prove that this works, I can go ahead and run my Python code and see I do go ahead and get the computations I would expect. Okay, I'm not necessarily going to spend the lecture time today testing each and every one of these solutions, but at any time, if any one of you stops and pauses and says, wait, what's happening there? We have the ability to kind of test. And one of the nice things about Python as well is that I could do intermediary testing to show you what's happening in between each step. So line by line. Exit out here. Let me clear this terminal and I'll relaunch Python in case we need that again. Okay. So I'm going to keep moving on until someone either stops me here in the classroom or if someone asks a question inside the chat. Can I just also ask someone in the classroom to also monitor the chat, because I kind of get a narrowed vision when I get into lecture mode and I don't necessarily look at the chat box as readily. So if someone does ask a question inside chat, please slow me down. Okay, so the next problem is very similar to the prior problem. We're just, instead of the OR though, we're looking to produce the bit and operation or the result of the bit and operation, but without being able to use the bitwise and operator. So here we have to do it with a negation operator and we have to use it with the OR operator. And again, we'll use De Morgan's law to do that same kind of translation, the transformation. So I'll take my X, I'll negate it. And for the purposes of breaking this logic down, I'm just going to save it in a new variable called not X. I'll take my Y, negate it, save that into another variable called not Y. I will then take my not X, OR it with my not Y, so that I have a result from that. And then I'll take that result and I'll negate that. And the negation of that will be the equivalent of what an AND operation was. So we can see we did pretty much an analogous thing. We just substituted the AND and the OR operators between those two problems. And again, this is actual code that if I wanted to, I could copy, paste it right in the terminal. I have some test cases here just to evaluate and ensure that it produces the results I would expect. And I can assure you, if I did that, it would produce the results that are in the comments. But I think with these problems, probably everyone has solved them already. So we're just going to move on, unless we have questions. Okay, let's look at the next problem. Our starter code is for the bit XOR. So here, what we want to do is we want to get the result of an X or Y, but limit it to only using the negation and the bitwise AND operator. And of course, our default implementation is just to return 2. So the way we can try to solve this is in a very similar way. We will do a negation on X, and we'll save that in our not X. We'll do a negation on Y. We'll save that inside of our not Y. Then we're going to take our two terms because there's a harder condition that we have to satisfy with XOR than with just OR, right? Keep in mind that the XOR property is that we get a 0 if both your first operand and your second operand is a 1 or 0. You only get a 1 if 1 is a 1. Yeah. So it's binary. So you have to have both elements of the set, right, represented in order to get a one result. Okay. So with that said, in order to satisfy that secondary condition, that more complex condition of the XOR, we can go ahead and do an AND between our two negated values and treat that, okay, that's our first term. And then we can also go ahead and do a bitwise AND operator on our non-inverted values on just our X and Y, and that's our second term. And so then the final result is obtained by taking the bitwise AND of the negation of the first term. So we'll negate our first term, and then we'll go ahead and also negate our second term. So that's going to cancel out those situations where they're both different or they're both the same, so that when we do this AND, it'll only produce a 1 if one is a 1 and the other is a 0. Excellent. Was everyone able to solve this one as well? Okay. Yep. Okay. Okay, so the next problem was is not equal. So here we want to return 0 if X is equal to Y inside of the parameters and 1 otherwise. So effectively, this emulates what our not equal operator would do. So again, our example is not equal 5, 5 would be 0, is not equal 4, 5 would be 1. Okay. So how might we solve this? What was the restrictions here? The legal operations were was clearly no equality operations, right? So we get to use almost all the other operations except for equality. The bang operation, the negation operation, the bitwise AND, the XOR, the bitwise OR, and then we could do the addition and then our left and right shifts. So how might we solve this? The first thing we would do is we can compute the bitwise XOR of X and Y. XOR will result in 0 if X and Y are equal, and non-zero otherwise. So here we do the XOR, and that'll give us the XOR result. And then what we'll do is we need to do a double negation using the not operation. So inside of Python, I can use bool to go ahead and effectively translate my result such that it then conforms to be a 0 or a 1. So if XOR result is 0, then by bool my XOR result, that will make it false, which I then can convert into an integer value inside of Python to make it a 0. If my XOR result is a non-zero value, I need a way to make it 1, right? So if I bool my XOR result, then that's going to make it true. And then I can convert that in Python back to an integer, which would then be 1. Because remember, one of the requirements is that my result is either a 0 or 1. This is one of those examples where there's a little bit more logic that I have the availability that I have to put in because of how Python handles numerical values versus how C does. And I have built-in Python methods, but there are operators in C that's doing the same thing that I'm doing here in Python. Right? So whereas I'm using bool to convert between a 0 and non-zero value to make sure everything is scoped between 0 and 1, I would have those same availabilities I'd have another operator that can turn a non-zero value into something that's equivalent to a 1.
Is bool another word for boolean, like short word for boolean?
Yeah. Mhm.
So they use bool in Python, right?
Yes.
Okay.
Well, I mean, remember, it's a loosely typed language, but there, when the type does reveal itself, yeah, usually it's in the scope of bool. So for instance, this is a function where you can pass a data in, and it's going to pass that data into a Boolean value, which is either true or false. Now, and then since Python is built on top of C, it has the notion that something that is a Boolean value can be rescoped into a numerical value as either 0 or 1 when we retranslate it into an integer. So, I mean, again, in Python, anything that's a non-zero value is considered true. But if we take a value and then pass into the bool function, it's now going to scope it to be either 0 or 1. And then when we recast it into an integer, it's going to rescope it back to a 1. Or I guess it scopes it to true or false. But then when you recast that into an integer, a true value into an integer, it scopes that to a 1, or a 0 value, or a false value into a 0, more precisely. Okay. Any other questions related to this solution? Okay. The next problem we looked at was, oh, this is our test case, was our copy least significant bit. So here what we want to do is we want to set all the bits of a result to the least significant bit of X. So the idea here is if I had, for instance, the value of 5 inside of my example, well, recall that the binary string of 5 could be represented as 101. Therefore, my least significant bit, in fact, the least significant bit of every odd number is going to be 1, and the least significant bit of every even number is going to be 0. Let me just make that statement. So if I select an odd number, say for instance 5, then if I want to copy the least significant bit for every bit inside of my value, inside of my binary string, then clearly I'm just going to have all 1s. And then if it's an even number, least significant bit is 0, then I want to set all the bits to be equal to 0. And of course, these are my legal operands that I have available, operators that I have available. And the max number of operations I can do this is in 5. So I'll also state that what if there will appear to be a violation in straight line code in this implementation, but that's in order to have Python ensure that this is a 32-bit int. Python does not have a 32. Let me show you something about Python so that you can very clearly understand what I mean. So do you recall what your min and max value is on a 32-bit integer?
Could you also take the number modulo to the 32?
You could, I mean, you could. There's multiple ways you can go ahead and do that, but I think that would kind of once you start introducing the modular operation, it might make the logic more difficult to ascertain. If I put the selection statement in there, then it's more readily understandable where I'm actually doing my 32-bit check, and then how I adapt for that. So I'm not saying you can't do that, but I opted not to. I opted to do a selection statement so it was very clear what the condition was, where I had to go ahead and truncate the number to be 32 bits, which is what I'm doing, right? Because I'm trying to emulate the logic for C inside of Python. So, oh, I'm already inside Python. That's why it says Python 3 is not defined. Okay, so if I go ahead and set a value of X here, and so what did we say was the biggest number inside of a 32-bit? Did we say? Is it? Oh wait, that's got some Q's in there. Okay, let's see. It's probably that's too big, right? Okay, now I can look that up, right? I can add like forward to that, and look, it went ahead and added 4, right? So one nice thing about the way that Python treats numbers is it's very fluid in its encoding, where it can very easily be a 40-bit integer value, right? Now, that is normally a awesome benefit of using Python, unless you're trying to emulate the behavior where your integers are constrained to 32-bit representations. So I added a little bit of logic in my proposed solution so that we can go ahead and have a answer that's in line with how you might think about this in C. So what you'll see here is I'm going to extract the least significant bit of X. So the best way to do that is to just take X and you AND it with a binary string of just 1, right? That way you preserve the least significant bit and everything else gets zeroed out. And then I'm gonna save that into a variable, LSB. Okay, so once I've done that, then I'm going to shift my LSB value to the most significant position. So we're assuming a 32-bit numerical value, right? That's what C handles. So I'm going to take my LSB and I'm going to shift that value. I'm going to do a left shift by 31 bits, 31 places. So now that'll shift it all the way across. Now, in order to mimic a 32-bit signed integer in Python, I'm going to do this quick check. So if my results and it with this actual shift, then I have to subtract from my results this shift, which is all the bits in front of it. So that's all I'm doing, is I have to unset the bits that automatically get toggled when I do this binary shifting in Python, because just like my ints aren't restricted to 32 bits, the whatever numerical representation I have isn't either. So this is just enforcing a concept. So this is something that mimics our 32-bit behavior, but would not go in your C code. It's a additional constraint that we're worried about. So we can ignore this when we're not in Python. And then once we shift that 32 bits to the 32-bit space, then what we need to do is we shift it back. So we'll take our result value and we'll take the bit that's in the forefront and we'll shift it all the way back. And recall that with an arithmetic shift operation, it'll duplicate across all those spaces the most significant bit, whether it's a 1 or 0. And so that'll allow us to go ahead and then result in a value that's either going to be all 1s or all 0s.
So is there a reason to hold the least significant bit in that first line?
Well, so the idea here is that I want to copy my least significant bit.
But if you shift it, it's going to end up at the most significant bit.
Mm-hmm.
Then you bring it back, or that's only because it's Python. That's
No, you have to do this.
Okay.
Yeah, so you take your least significant bit, you shift it to be the most significant bit so that it's in a position when you use your right shift that is going to duplicate the most significant bit on every bit that is shifted across to preserve the sign bit. Remember, one of the advantages, so you have a logical right shift and you have an arithmetic right shift.
Right.
And the arithmetic right shift preserves the sign bit, which is our most significant bit. So if we take our least significant bit and we shift it all the way so that's the most significant bit, and then we use a right shift, the arithmetic right shift, which is the default right shift, to go ahead and shift it back, then it's going to duplicate our most significant bit for every place that we right shifted. So like if we right shifted 3 spaces, then the spaces in between the third space that we wanted it to and its original position will be filled with whatever it was, because it's trying to emulate that sign. So if it's a 0, it's a positive.
I get that part. What I'm saying is, the least significant bit is the least significant bit, whether you mask it or not. Well, I guess that's not really true mask, but right, it's still a 1 or a 0, no matter what.
Yeah, that's right.
And if we shift it left, it dumps everything else out, and we're just left with a 0, 1,
Mhm.
and a significant bit.
Yeah.
And that's not even using that first line. It's irrelevant.
Oh, yeah.
I didn't know if there was a reason. To me, it seems relevant. I was asking if there was a reason that I didn't see, and I assumed it was because Python, if it did have 40 bits, if we pushed it, there's
Yeah.
those 8 bits left. This would have eliminated those 8
Yes,
bits.
yes, yes. Very good question though, and it's going to illustrate why there's a showing Python solutions really going to challenge how we think about this in C, but how we also think about these solutions in a different language as well. Which hopefully a byproduct of this will have you start thinking about how you can use Python moving forward as well, which is a very popular language in cybersecurity, system programming concepts, system programming in general, and data science. Yeah, Python.
It overtook Java last year.
Yeah,
Higher than
has everyone touched Python for the most part in this class by now?
I mean, personally, it's not here. Automate boring stuff.
Yeah, I mean, Python is there's definitely good arguments as using it as an introductory language.
Good free book. You can buy a free copy of it also. Free press called Pink Python. I think Stanford uses it as that's where it started with Stanford using it for their comp sci program. And Green Tea Press offers the PDF download for free, or you can buy a hard copy for Riley.
I mean, even Dytel and Dytel's newest books that they have released, their most recent ones have pivoted to Python. That follows the same kind of chapter organization that 1583, 2120 books do, but they also introduce data science and data analytics as a portion of that as well. Yeah, we're not there yet inside this curriculum, but I think we might be discussing that, like what would be a good introductory language. And I'll be honest, there's good arguments for keeping it Java or something Java-like, but there's also great arguments for pivoting into Python. And like this kind of gets away from the data lab, but one of the reasons why I think it would be good, an argument for teaching Python very early on to our computer science students. Well, not just our computer science students. I think the thing about Java. So this is the thing about Java, or C# or another language similar to that, because those are kind of analogous to one another. Those have value for someone who actually knows ahead of time that they want to go into software development, right? There's a lot of tooling. There's a lot of wealth of assets that's built into that ecosystem that a lot of industry bank on using to build scalable code bases, like code that spans, like you would never want to write an application in Python that spans hundreds of thousands of lines of code or millions of lines of code. That would not be a fun endeavor. In fact, what happens when you start scaling Python code to that level is you start getting things like Java and C#, and you start building a lot of technologies that start adding strong typing and building tools, and you have your linters and a lot of other things that have to then like add into the complexity that kind of a scripting language allows you to avoid. Scripting languages are good for simple, fluid tasks, but for large-scale software applications, that's the real value of where a language like Java or C# really comes to shine from. So it's a good language for you to know to build really robust, large-scale applications. That's one value for that, right? But really, a language that's built for that purpose and is so difficult to use for simple problems, right? When was the last time someone built a Java, just in this classroom, like nominally, when was the last time any one of you built a simple application just to solve a problem you had to automate a task using Java? And that's the language you took like 2 or 3 semesters learning the most. And you probably still come out and like, that's a clunky language. There's a lot I have to invest into just to get any result out of it. Now, the advantage of it is that it scales incredibly well, right? And that's like when you're building, when you're like in enterprise level software development and application development, that's where like there's a sense to it. But in a very small scale, small stakes environment, it's the verbosity actually detracts from its use case. So like, and that's where you come in with the argument of Python. I can get so much with so little, and I can automate almost anything such that I don't even have to know that I want to go and become a software engineer to be able to say this language is worth learning. I could learn this language and just solve basic automated tasks that I encounter daily, whether I end up becoming a business major or a chemistry major or a biology major or an engineer or an educator or an actor or a musician, right? Like I can use Python to make any task in any other domain solve. So I think one of the nice things about talking about Python in terms of an introductory language is it opens the door of the use case for it outside of just priming you for enterprise level application development. And it gives you a tool that allows you to start to automating actual tasks in your life away. Anyway, that was a big sidebar. But that was my thought on Python. Okay, let's go back to our oh, so that's why there was one of the constraints. So this one was special bits. Here, the idea behind this puzzle was we had to return the bit pattern FFCA3FFF. Now, remember, one of our constraints was we couldn't operate on something larger than, what was it, an 8-bit constant value. So you have to figure out how to use an 8-bit constant value, do operations, bitwise operations on it in a way that produces this 32-bit binary pattern. So that's what the question was really intending to ask. So the idea then is, if you know that that's the case, let's look at this sequence here as our inspiration. So we're going to translate our hex into a binary string. And when we do that, we can then say, okay, based off of that, this is so we have all ones on up to this point, and we have all ones up to this point. So what is the string that we're interested in? This is going to be the binary string that's most interesting that we'll have to use as our basis. D7, binary string, right? Which can be represented as 11010111. Okay, so this is the size constant we're allowed to have access to. Now, if I shift this 14 spaces, 14 bits to the left, notice now I have every place where I would eventually, when I have a 1, I have a 0. Here, every place I eventually, when I have a 1, I have a 0. And then here, inside of our sequence here, every place, because I selected D7 so that I can negate it to be the bit pattern I want in the middle. So then once I do that shift, I can do my negation on that, and that's going to produce an outcome that produces the binary sequence we were looking to do. Does that help explain what the motivation was more so with that? Okay.
The instructions for that binder of that 8-bit communication binder.
Yeah. Okay. That's good. Yeah.
And then somebody in this school had a question about this one.
Oh, what was question?
I think we were asking about.
Oh. Yeah, I have the meeting chat open, but I don't think I have Discord open. So if you do have Discord open. Well, we can circle back around. Or if you could post your question inside the chat, which I have open. Okay. So the next one after that one was the conditional operation. The conditional operation is the only ternary, it emulates the only ternary operator that's inside of Java or C++ or C, right? The idea behind this operation is that the X value represents something that is a Boolean expression. So if it's 0, or it represents a false value. And if it's a non-zero value, it represents something that's true. And then I resolve either the Y or Z, depending on whether it's true or false. So Y is what I would effectively evaluate to on the instance that my X was true, was a non-zero term, and I resolve a Z value on the instance that my X term was 0. And again, the legal operations we have are going to be the ones that don't allow us to do a ternary expression, right? We're trying to learn how to build that with these bitwise operations. And just a good way of trying to express what the logic is, I'll try to do this kind of briefly because we're already at 5:57. Should have taken my sidebar. So let me know if any of this does not make sense. So given our X, Y, and Z, we're going to check to see if X is non-zero. So if X is non-zero, then what we can do is we can check, we can do our not X and convert that into an int. And then what we can do on top of that is add to the result of that the negation of 0, which is the same as saying 0 plus -1, which will result in a -1 term. So this allows me, at least with Python, to be able to use my X, if it's non-zero, to get a -1 term, which would result in a binary string that looks like this. All ones. Okay, so if my X is 0, then if I not my X and then convert it back into an integer, that would be 1. So then if I take that evaluation and then add it to the negation of 0, that's like saying 1 plus -1, which would be 0. So that would result in a binary string that's going to be all zeros. So I'm going to use that to effectively make a mask. So on the instance then, that so with my mask, if X is non-zero, I'm going to get a binary string that's all ones. And if it is 0, then I'm going to get a binary string of all zeros. Okay, so then I'm going to use that mask to select either my Y or Z value. So if the mask is all ones, I can do Y and then my mask, and that will be my Y value. And then if I take my Z and I and that with the negation of my mask, that's going to zero out the Z term so that it's 0. So that would result in a value that's just Y. On the flip side, if my mask is all zeros, then when I take my Y and it with the mask, it's going to zero out the Y value or the Y binary string. And then if I take the Z and I bitwise and it with the negation of that mask, then that's going to result in my Z value. So then all I have to do is with my mask, I and it with both Y and Z, but one of the instances I AND it with the mask and the other I AND it with the negation of the mask. Seems pretty simple, right? And then I just go ahead and select the OR between that. Since one will be all zero terms, whichever one is not the all zero terms will be the result that I'm looking for. Excellent. And again, just to convert this into a 32-bit solution, I go ahead and then just AND that with these with a 32-bit string of just ones. So that all my higher end bits in my inside of my Python value go away. Okay. The next problem we had to encounter was bit parity. Here, we want to return 1 if X contains an odd number of zeros. So say, for instance, the bit parity of 5, which is represented as 101, would be 0. The bit parity of 7, which would be 111, would be 1. And I think this one was rated as one of the more difficult ones, right? Was this? I don't remember. But the idea on how we go ahead and achieve this is the goal is to compute the parity of the bits in X. The parity is 1 if the number of ones in the binary representation is odd, otherwise it's 0. So what we'll do is we'll iteratively reduce the number of bits to consider by XORing our blocks of bits together. So XOR has a property that 1 XORed 1 is 0, or 0 XORed 0 is 0. But if 1 is XORed to 0 or 0 is XORed to 1, it produces a 1 result. So this effectively lets us add bits together without counting the number of ones. So then the actual implementation we have here is we could take our value and we XOR it with the value of X shifted by 16 bits to the right. So effectively what this does is it XORs the top 16 bits with the bottom 16 bits. And then we iteratively do that. So then what we'll do is we'll now take the top 8 bits of the result and XOR that with the next 8 bits. And then what we'll do is we repeat that process, reducing the number of bits in half each time, 4, 2, and then 1. And then finally, at this point, we'll go ahead and just get the least significant bit of X in the parity. And of course, doing a little bit of Python to ensure that my bits over 32 are zeroed out. So let me see. I think I gave a better, in case that was difficult to understand. Did everyone get this one right? Okay. In case my first explanation was difficult to understand, I wanted to actually get an example to show you what's happening with those iterative calls of doing the shifts, these right shifts, and XORing. So let's look at an example. So suppose that this is my 32-bit string, right? It has 16 ones, so the parity should be 0. That's even, right? Okay, so the result of this should be 0. How can we evaluate that based off of these operations? Well, I'm going to XOR the top 16 bits with the bottom 16 bits. So this operation, which was the first operation inside the Python code, would be to take this, the first 16 bits, and XOR it with the bottom 16 bits, which is going to produce this result. Then what I can do is the bottom 16 bits remain the same for now. So we'll now XOR the top 8 bits of the result with the next 8 bits. So if I go ahead and do this operation, that's the equivalent now of taking our top 8 bits and doing that with the next 8 bits, which would produce this binary result. And so now the bottom 16 bits will remain unchanged from the prior operation, from the shifting. And then we continue that process until we reduce the number of bits by half at each time. And you see, as we do that, we keep reducing down until we finally resolve to a value that will result in either 0 or 1. And 0 if we had bit parity, or 1 if we did not have bit parity. Does that answer the question? Or does that kind of make it a little bit more understandable what the logic is? Kind of seeing an example broken down. I think that was the last one we had in the logical puzzle. I think that was like the capstone one of the logical puzzles. Okay, so the next puzzles after that were our arithmetic puzzles. So the first one was to go ahead and produce a value that was -1. And of course, these are our legal operations. The max number of operations you can do is 2. So clearly the easiest way to do that is you just negate the 0 value. Like you use your constant value of 0, negate it. And that's going to go ahead and produce a -1 term for you. So if we want to go ahead and find our T max, very similar, we can go ahead and take our value of 1. We left shift 1 32 times so that we create a bit binary string of all ones, and then we just go ahead and negate that to be the highest integer value, right? Signed integer value that we can represent. Okay, if I wanted to go ahead and represent negate using these basic sets of operations that I have available to me, what I could do is recall using a using 2's complement, I can get the negation of my binary string and add 1 to it. Okay, if I want to check if a number is negative or not. So I return 1 if x is less than 0, I return 0 otherwise. What I can do here is I can take my value of x, I right shift it by 32, and then I bitwise AND it with 1. And this will effectively allow me to go ahead and check whether the term was negative or not, right? Because recall that this is the part here that is more important. This part is helping me with some Python translations, right? We're taking the most significant bit and we're going to go ahead and shift it to be our term that we care about. Okay, let's see here. The next problem is positive. And here we can do a couple of different checks for is positive. So there's 2 conditions you have to check to see if something's positive. You have to see if x is non-zero, or you have to check to see if x is non-negative. And so we can do this by, we can do one check to see if it's a non-zero term. And then if it's a non-zero term, we could also check to see if it is a positive sign by doing this right shift. And then we can just do a bitwise operator between whether it's a non-zero and if it is a positive sign. And that'll tell us whether the number is positive or not. For the bang operation here, we want to try to go ahead and compute not x, or the not x without using the bang operator. So was everyone able to solve this one? I think this one was evaluated as a difficult one as well. So the concept on how we could go ahead and solve this is, given an x, we can take the 2 complements negation of it. So we negate it, add 1 to it. We'll call that our negation of x here. Then we could use our bitwise OR to combine our x and our negation of x. So if x is non-zero, either x or the negation of x will have the most significant bit the single bit set. If X is 0, both X and the negation of X will have the sign bit unset. So then we can right shift by 31, which will either produce all ones in the binary string, which is -1 if the sign bit was set, or all zeros in a binary string if it was unset. Then we can add 1 to the sign bit, and this effectively computes the logical knot of X, since -1 becomes a 0 and 0 becomes a 1. Let's see. I think the next one was to add OK. You determine if you can compute X plus Y without overflow. So remember, with overflow, it's not only summing two very large positive values, but trying to sum two very large negative values. So what we can do here is we can take our X and we can add to it our Y. So we create our sum value. Then we can XOR between our sum and X, as well as between our sum and Y, which will produce a number with the most significant bit set to 1 if the sum has a different sign from either X or Y. If both X and Y have the same sign, but the sum has a different sign, then this means that there was an overflow. By performing bitwise AND between the two results, we can determine if both conditions are met. Finally, we can right shift by 31 and extract the most significant bit. So that's our sign bit of the result. So effectively, this is the expression that would result from that. So again, we take our sum value and we XOR it with our X, take our sum value, we XOR it with our Y, we bitwise and that together, and then we shift that 31 bits, and depending on the result will tell us whether we had an overflow or not. And you'll see that in the test case for this, we would either get a overflow on either very positive or very negative values. It's a little bit more difficult to make negative values in Python. You see, I can either, so I just use the integer value here. And then I think, was this the last one? Abs val for at least the arithmetic operations. And of course, what we want to do here is just take the absolute value of X. So the way we could do that is we can shift our X 31 bits to the right to extract the sign bit. If X is positive, the result will be 0. If X is negative, the result will be a 1. Like it'll be all ones in our 32-bit 2's complement. So we're going to do that. We're going to take this, our value of X, and then we'll right shift that to 31 places. Then we're going to check to see if it's effectively positive. So if X is positive, then what we want to do is take X, shift it to 31. If it's positive, remember that's 0. So 0 plus X. So a term with all zeros, if take the sign bit and you produce a result that is all zeros, we add that to X. That's just going to be X. That's going to remain the same. So if we then XOR that with 0, that would be X. So if X is negative, then that would be effectively X minus 1. So the final result that we can do would be to do the XOR between these two computations, right? So we can add our sign bit to X, and then we XOR it with the sign bit, and that'll go ahead and drop the negative sign to get the absolute value. And of course, this part here just goes ahead and ensures a 32-bit mask. Excellent. And then the last were the bitwise puzzles. But those were all the bonus problems. Those are the ones you get to do for fun. Excellent. So does anyone have any questions about those? Now, quick question. Do you have a preference on going through labs in terms of the problems like this, or do you prefer just going over the content of the book and working on labs in your own isolation? So this is a kind of a trial run since everyone had a chance to touch Data Lab. I actually reopened up the due date for Data Lab 2 because I think I had forgotten to do that last lecture on Thursday. So it'll be due on Friday. Next lecture, I'll start walking through the GDB using the next lab, which will be the bomb lab, as the basis for that. So that we'll walk through how to do the bomb lab, and then you all get to do it on your own with your own bomb that gets generated for you. Excellent. So I will see you on Thursday. Yeah, so I'll post the chapter 3 slides. I'll probably also post these slides too, if you want, if you find value in these, with the exception that I'll have to remove the C code ones. Because I have my solutions on this particular one in case there was any questions for actual problems that the Python didn't reveal. I had C representations that I could default to as well, so that you could actually see the answers that would score you the points. I'll remove those from the slides I share. Excellent. Any other questions?
So once again, those will be posted on Discord.
Yeah, these slides. All the ones we just covered today. Yes. Any other questions? I will see you on Thursday when we take and learn how to use the GDB with the next lab. And I'll obviously also get that lab published as well, but we'll walk through it the same ways we walk this lab. And I'll probably maybe start using the labs as our vector into the material, as opposed to using the book, because I think the book can be dry at times. And then hopefully, if it's on a lab you haven't been working on for weeks, you can actually log in and kind of work alongside so as well. Okay, I will see you all in 2 days.
Alex.